Thanks very much for the introduction. And yeah, very, very glad for the opportunity to talk about this NSF funded project and the machine we are almost about to bring to the community. So, still maybe a few more weeks. So yeah, thanks very much to the INC talk organizers and giving us the opportunity. I have some of my SDSC colleagues here. I can see some of whom are directly involved with the Voyager project, so that's good. They can help answer the difficult questions, as well as some other colleagues whom I work with from SDSC, right? So Kenneth Yoshimoto and Young Trung, with whom I work on the neuroscience side, with the Schwartz Center for Computation Neuroscience. And from the SDSC side, people who are directly involved with the Voyager project, and Mahidar Tatineni is director of the user services, have a lot of experience with architecture and implementing algorithms, codes, benchmarking. And Paul Rodriguez, who is a data scientist and involved with the Voyager project. Okay, so I'll quickly start the presentation. So let's see, the title is Voyager Exploring Havana Processor-Based AI-Focused Hardware for Science and Engineering. And let's see. So I'll give an overview of the Voyager Award and then talk about the Voyager system architecture, which consists of, custom built for AI. So that is the key word of this presentation, is to keep in mind that this Havana training nodes called Gaudi and the Havana inference cards called Goya are ground up specifically built for AI only. So it will only work for AI frameworks. That's the key part of this presentation. And I'll explain how that all fits within the context of this NSF award and everything. And that's the exciting part of science and engineering. So it's not a general purpose machine which is doing AI very well, just like the GPUs does AI very well, but general purpose. But this is built only for AI and specifically training nodes and inference nodes for training and inference. So that's what we want to explore. So that's my outline of the talk. A quick, maybe it's not needed, but I'll mention quickly, the San Diego Supercomputer Center is one of the first few, maybe first 5 academic supercomputer centers established by NSF in 1985. I think this is known to most, so I'll just quickly jump through these bullets. It obviously serves the national community as well as UC and UCSD. The researchers who use the supercomputer server infrastructure and data resources comes for any and every field of science, engineering, social science that you can, even people from music school analyze dance videos with AI and astrophysics. You can name any and every science, engineering, social science. Obviously, among various other things, we design, architect, and deploy large-scale supercomputers and data resources. And SDSC researchers, like many of them who are in the call, have they wear another hat where they're as a scientist, they write proposals to NSF, NIH, DoD, and do research. And we have a data center. So now quickly jump to this category 2 award. So let me quickly explain what the category 2 award is. I think that will fit well with the context of the whole talk. So, so whenever we say category 2, that implies there is a category 1 award. NSF, so the Office of Advanced Cyber Infrastructure issues these calls. So let's talk about the category 1 award or the call. For the category 1 call, you propose a supercomputer that is ready to go on day 1. Means you are not, experimenting with new architecture, new hardware, new software stack, new programming models. It's say you buy the GPUs or Intel or AMD processors, and that will work on day 1. It will be a large supercomputer. The software stack from the system side, all the applications, we have hundreds of applications from math to molecular dynamics to, biochemistry to MATLAB. Everything will work on day 1, and scientists will be able to do science across all the domain sciences on day 1. So that's a category 1 award. It should work for scientists to do science. So which is great. And we got a category 1 award just before, a year before we got this category 2 award, where we call the machine Voyager. And the category 1 award is a AMD EPIC processor based and NVIDIA GPU based machine with a huge, petabytes of luster file system and all those things. So So that machine has been there, expands, and Mike Norman is the PI of that. Actually, I think Mahidar is a co-PI, I'm a co-PI, many people are involved. So now NSF created this category 2 call, where they want you to be innovative. They want you to be innovative, whatever that means. You can be innovative you can propose a new architecture. The people have proposed and they have been funded like ARM architectures for HPC. You can propose new ways of doing maybe data science, or you may propose even distributing computing all across the nation. So something new where you can, the architecture could be new, way of doing science could be new, or a new twist on ARM architecture, pushing it to solve scientific problem could be new. So that's NSF, the mandate is for you propose experimental machine. So where you can be innovative. And so in this, so that's where we responded with Havana's training and inference AI specific hardware as the Voyager machine, and it was funded. So, so it's a $5 million for the hardware, and then 6.25 million for 5 years to collaborate with scientists who want to use the new architecture, which is not available in the market. So everything in architecture is new. The software is, should allow scientists to do science, but you can optimize things as you go along. And so that's the idea of an experimental machine. And here, I'm the PI, and many from the UCSD, SDSC, like Romy, Javier, Mai, Bob, are the co-PI. Sean is the project manager. We have external advisory board, a lot of science use case researchers, and I will talk about them in detail towards the end of the talk, are part of the, helped us write the proposal, and then we will work with them as soon as the machine is available in a matter of weeks. And then obviously we have the SDC HPC system side with a lot of expertise in bringing large scale machine, and they are excited because we are first time kind of trying with innovative new architecture, network security people, education outreach, and then Mahidar Tatineni, who leads the user services, a lot of expertise there in understanding applications, benchmarks on current and new architecture. I'm so glad to see Larry Carter. We have learned from him so much for decades. We took his classes even when I first joined SDSC. His I think performance optimization, all kind of things we learned from him. Okay, so that's the overview of the project. So now, given it's a experimental machine where we'll explore a AI-focused hardware for AI application in science and engineering. So we have set it up, the project, it will be a 3-year test bed phase, which means where we will kind of select researchers from the community, and many have already contributed to the proposal, and you will see their names and their science cases later in my talk. We will work with them to implement their AI applications on the training and inference nodes of this Voyager machine, which is Havana's processor-based machine. And given it's an experimental machine, a lot of things we will figure out for the community, with the community, and that is okay. So it's not everything will work at the optimally on the first day. For example, the TensorFlow implemented on the Gaudis, we may find for some AI models, some of the operators are not optimized, but then we will work with Havana to provide input, and they will optimize those operators for the TensorFlow application of a PI. And so that's what I'm trying to tell you is that that's a different mode of operation than a category 1 operation. And that is the excitement part of a new architecture, software stack, and application scientists. So that's what we will do in the first 3 years with a select group of scientists. And I hope some people who are here would be interested in using the machine and work with us. And obviously, I'll talk about the training processor, inference processor, and the storage. And then initially, we will work with the frameworks of TensorFlow and PyTorch, which are working on the Havana, Gaudi, and Goya. But it also allows custom development of application. I'll mention it briefly. But then on the last 2 years of the project, it will open up through the typical how category 1 machines are made available, which is where you write a allocation proposal explaining your science and justification for the time you need on a supercomputer, which could be tens of millions of hours or hundreds of thousands. it goes through a national peer review process. And out of that process, we, the people who are running the supercomputers, are told, okay, these are the scientists who got time this much on your supercomputer. So who uses our machine is not in our hand at that point. It goes through a national review process. So last 2 years, this Voyager machine will become like that. But anyway, but overall, the impact and engagement, the Voyager's scalability for large-scale model is a new architecture, probably one of the first, just AI-focused hardware. There are other machines like that, the Cerebrus at Pittsburgh Supercomputer Center. Anyway, so we want to engage with the community and do exciting things on this new architecture. I think I've already mentioned this first years of test-based phase where we evaluate Voyager's innovative deep learning hardware, software libraries for different domain sciences, focusing only on AI application. It's only AI-focused hardware. And then the last 2 years will continue. Many of the things we learned from the first year in the training, outreach, documentation, benchmark, optimization will carry over to the 2 years. We have planned for and budget for 2 workshops every year. So although it's evolved around Voyager, we want to get engaged with the AI community in general for Voyager's sake, and also in general for the future of SDSC and AI community, and to learn more. So now I will talk about the Voyager architecture and the software. So again, it's Havana training nodes are called Gaudi. They're specifically for training, optimize TensorFlow, PyTorch to start out with, optimize on the Gaudi. And it has a software suite, is the Synapse AI Software suite. And then Havana inference nodes, they are called Goya inference processors. Okay, so a quick intro about Habana. As was already mentioned during the intro, it was founded in 2016 to develop purpose-built AI processors. They launched inference processors first, and then training processor in 2019. It was acquired by Intel in 2019, so it has all Intel's support and research and expertise, experience, and they made the Gaudi AI processor is available on AWS. So DL1 is the Gaudi processor available on AWS. So, and also we have been working very closely with Havana, and some of the slides I will show have been shared by them. So thanks to the Havana team. Now, Supermicro is a company maybe some of you know, but let me briefly mention. They are like Dell or HP, they integrate and basically build the supercomputer for you, in this case for SDSC, so we can make it available to the community. So they get the, Havana processors from Intel Havana, they get to buy the storage from someone, and then we have a big 400 gig Arista switch. So they put all of these together in their racks with the power and management nodes and everything. So basically, it's a 3-way effort, Havana, Intel, and SMC and SDSC. Even when we wrote the proposal, we sat down with these 2 groups of people and experts to design the machine. And other input, obviously, was all the science applications. What are their needs? What kind of AI frameworks they use? What is their data need? What is their current research and future? So we look at the science, so it's kind of a co-design, the science applications, and then the processor from Havana Intel, and then with SMC. So it's a 3-way effort to write the proposal. And the constraint is obviously the $5 million budget that NSF provides. So how much storage, how much training, how much money should we spend on training to get the Gaudi nodes? How many Gaudi nodes should we get? How many Goya processor? How much storage? How much, the Arista switch is expensive. So anyway, so we write all of these, all justified by the science applications, which I will talk towards the end, and write the proposal. And we are happy we got funded. So we have been working with these 3, us, actually 4 groups, like us, the application scientist, the Havana team, and the SMC. So I'll jump right into the Gaudi. It's designed for compute efficiency in AI training. First, kind of a new from purpose-built ground up for optimizing AI training. And so you have the Gaudi from Havana, and the Synapse, and I will talk about Synapse later, is the software suite. And then Supermicro puts all of these together in their X12 Gaudi AI system, which you can buy, anyone can buy today, just like we bought. And then I'll explain about the SDSC specific Voyager machine, just its technical specification. So that's the Gaudi. And this is how it looks. And I have a few other slides explaining a little bit more and the network. So basically a Havana Gaudi server is a 4U system with 8 Havana Gaudi processors per node. So that's the important information. You have 8 Havana Gaudi HL205 processor per Gaudi server or per Gaudi node. Again, it's built for AI and deep learning. And another very key, and really one of the key things is a built-in 400 gig this quad SF double density ports, and I will show them in a few other pictures. So that's very key of the network design of our Voyager machine and any Gaudi based machine. And so obviously they have this CPU. These are Intel Ice Lake CPUs and memory that comes with the Intel nodes, which is a host for the Gaudi, as I said, 8 HL205 Gaudi AI processor per Gaudi training node. So here is a little more picture of the Gaudi servers. So the important thing is this number 6. You can see 6 QSFP DD connectors coming out, and I will explain the network, how network architecture of the Gaudi and Voyager, and you will see 2400 gigabit Ethernet connection coming out from each Gaudi server, which is then goes to the Arista switch, and that's how we scale across Gaudi nodes. So remember, each Gaudi node has 8 Gaudi AI HL205 processors, but then from node to node, we scale 2400 coming out from each Gaudi server or node to the Arista switch to scale to other Gaudi nodes for large scale data parallel modeling. Okay, so that's that. Yeah, it's the kind of the same picture with a different view. Again, you can see these 6 QSFP DD connectors coming out of each Gaudi node, and that will be part of my talk towards the few more slides when we explain the architecture. So now going back to the Gaudi architecture, it's built for performance and efficiency. You can see the TPC cores. They're fully programmable with tools and libraries. They have a matrix math engine, and they have a 32 gigabyte high bandwidth memory. And again, the last bullet is very key because for the scaling, and that is one thing we're going to experiment with this Voyager machine, I'm sure with the science community and even the computer science community. It's 100 gigabit Ethernet natively integrated. So that's a key thing. And it's with the Rocky protocol, RDMA over Converged Ethernet. So remember this 100 gigabit connection coming from each Gaudi processor. So let's go to the next slide. So yeah, and the overall idea is these three columns you can see. So usage point of view, from the user point of view, we will first have users who are using already their AI pipelines using TensorFlow and PyTorch. These are already integrated with the Synapse AI software suite, and they create the the graph compiler. It creates various graph components, and many of them, and depending on the model, maybe all of them are already optimized for the Gaudi architecture that I had in a brief slide in the previous slide. So users don't have to do anything. That's just few lines of code change, few lines to maybe just a few tens of lines in the worst case, and when they're using, they will be able to use their TensorFlow and PyTorch implementation and use the same abstraction of those frameworks and get the optimal performance of this purpose-built AI training architecture. But it also, Synapse AI software development kit will also allow customize development for custom kernels for people. Maybe that will be the little down the road for AI researchers who want to go outside of TensorFlow and PyTorch. That's abilities there. We will experiment with those, which is great. Experimental category to allow us to do that. And then you have 32 gigabyte of high bandwidth memory. So codes that are running on GPUs, should be able to fit and run. So that's from the users like a point of view. Now, going back to the scaling efficiency, this is a big part of the, in general, Havana's architecture, and which we have carried through in the Voyager architecture. So this is industry's first native integration of 100 gigabit Ethernet Rocky ports onto every Gaudi. So, and I will explain how the connection is probably in the next slide. But it eliminates the network bottlenecks and is standard Ethernet. So there is no locked-in proprietary interfaces. So that is important for scaling large AI models across Gaudi nodes. So that's a very important part. And it's a standard Ethernet Rocky protocol, so nothing proprietary. So this is how it looks. So here you can see 8 Gaudi processor like 0, 1, 2, 3, 4, 5, 6, 7. Each one of them have 100 gigabit connection coming out. And see these blue lines, like on number 3, it's going to the right, number 2 going to the right, number 7 going to the left. So these blue lines are 7 out of those 100 gigabit Ethernet connection goes to the other 7 Gaudi AI processors, right? So there is a non-blocking all-to-all internal interconnect across all Gaudi AI processors. So out of the 10, 7 goes to the other 7. So that leaves 3. You can see the black lines coming out of number 3, 2, 1, and 0 to the left. Those are then the other 3 100 gigabit then goes out to this 6 QSFP DD that I showed you before in the diagrams. So they all go there, and then they go to a 400 gig Arista switch, through which it goes to then another Gaudi node, which also has the exact same architecture with 8 Gaudi AI processor. So that's how the scaling is done. And it's all, both internal and external are the Rocky, RDMA Rocky. So that is very, very nice for scaling and the cost and everything. So that's a key part that we will explore as we get into this journey. Yeah, I think this is showing the same thing. You see the 8 HL205 AI processor. This is within a Gaudi node or a server. And the red lines are the 700 gig going to the all-to-all. And the green lines are the 3 out of 10 that are left from each going to this 6 QSFP DD connector, and through which it will go to the next to the switch, just like you see here. Now we are seeing, each one of these is a Gaudi server, a Gaudi node with 8 Gaudi processors, and then the 6 400 gigabit E per node, because 8 times 300, right, 2400 coming out of each. So that's 6 400 gigabit E going to this Arista switch, and everything is natively integrated Rocky both inside and outside. So that's very interesting how the scaling works. I'm sure scaling will be one of the things we will explore. This is basically saying the same thing. So we have Supermicro X12 8 Gaudi server, which is each Gaudi with 8 Gaudi AI processor. And then for inference, we have 2 inference nodes. So we have 42 Gaudi nodes, each with 8 Gaudi AI processor, and we have 2 inference nodes, each with 16 inference processors. We talk to the science community and use our own experience, thought process, and the community and the money. As I said, $5 million. How much training to get, how much inference to get. There is storage, there is switch. So we just have to make a call. That so 8 So we have 42 of them with 8 Gaudi AI processor per node. So we have 336 training Gaudi processor and 16 inference Goya processors. Okay, so now this is the Synapse AI software suite from Havana. So again, the framework integration layer will allow AI scientists who already have their application in TensorFlow or PyTorch, and they may have others down the road, but initially TensorFlow and PyTorch implementation, and that will go to the framework integration layer. And then it has the kernel library and the graph compiler. And then, graph compiler will break down all the graph components. And as I said, depending on the model, either all of them or most of them are already optimized on the hardware of the Gaudi. So users will right away able to see the performance of the Havana Gaudi AI architecture. And so that's what we will exactly start our journey in a matter of weeks. And then custom kernel libraries there, so advanced users can write their own custom kernels that we will explore down the road also. And it has all the debugging and profiling tools and programming tools, and it has its Havana communication library that it will use to communicate across the AI processor within a node and as well as across the Gaudi nodes. So all of these we will explore. Yeah, I have looked at some of their training. It seems they have very good profiling tracing tool. I was looking at some even yesterday. It's pretty detailed, just like any other tracing and profiling to the level of tau and others. Let's see. Okay, so the Synapse AI software, I think I talked about all of these already. Graph compiler, runtime optimizer. Yeah, it generates optimized binary code to implement on the top layer of Gaudi, and all shielded from the users. Users are not worried about any of these. They're just running their TensorFlow and PyTorch on Gaudi, and just as I said, few lines, basically module load Havana and another line to just tell the TensorFlow, hey, you're going to run on a system called Gaudi, and so things like that. And then communication libraries for scaling accurate Gaudi devices. Okay, here is one little, just one example to show how easy for a simple code it will be to run on a Gaudi device. Basically, I think these are the 2 lines that you have to add to your TensorFlow code. Load the Havana libraries. Needed to use Gaudi. I think HPU stand for Havana processing unit or something like that. Basically, the the Gaudi device. And once loaded, it is registered with TensorFlow and prioritized over CPU. So as I said, it's a new architecture, and Havana software stack is optimizing various models and operators. So in case, most of them will be optimized for Gaudi. But in case an operator is not available on Gaudi, then it will run on the CPU. So the application will still run, and then maybe down the road in a matter of days, 2 weeks, Havana will optimize that operator on Gaudi, and then all of your code will run on the Gaudi. So that's the experiment we get to do on experimental machine. So yeah, and this is Havana's developer platform, which is all the detailed information of a lot of the things I talked about, but more from a user's point of view, what to insert in a code to like identify like the device and things like that, how to run across Gaudi cards, how to run which models are already optimized, which operators are already optimized, which are going to be optimized in the next few weeks, and some are maybe down the road in a few months. So all those detailed informations are all there. Initially, their focus has been on vision, like ResNet and NLP, BART, this kind of, initially they have targeted vision and NLP. I think there are some other models are also happening. Given it's a new architecture, new software stack, these are all need to be developed and optimized. But all those informations are there in detail, as well as the trainings. And we will do our own training on Voyager as soon as it's available. So let's see. So these are the some ResNet number that SMC gave us maybe towards the middle or end of last year. And again, we are, as we speak, the machine is made available to SDSC research. It has been made available for last few weeks. So we are rerunning all of those. And but here I'm showing what SMC gave us, and you can see linear scaling across Gaudi nodes. Again, each node has 8 Gaudi processors, so 8 nodes means 64 Gaudi cards. Let's see. And so this was published by Havana just sometime in December, probably even. And there you can see their ResNet and BART numbers and the version 1, how they have improved going to version 1.1, and then the scaling or time to train. So this was run on Gaudis that Havana have in their lab. So not on Voyager yet. We are literally doing these things as we speak on our Voyager machine. And so yeah, it will have now going back to the inference part. So that was all Gaudi, which is the training. So Goya is the inference processors. We have 2 inference nodes with 8 Goya processor on each, and it's optimized for inference workloads. It will have the same Synapse AI software. And a lot of their published results are available on white paper and benchmark results, both for Gaudi and Goya from Havana's website that you can check. A lot of technical information in detail there, of course. Let's see. So these are the numbers that Havana recently published on Havana website for BART and for Goya for different batch number. The latency is low, high throughput, for different batch sizes. So this is what they have published. And again, we are doing literally all of this ourselves now that we have our own machine. And just before we make it available to the community. That's also part of testing the machine, making sure the machine is working well and the way it's supposed to be. All the hardware, software, and the complicated network, all of those we are going through right now. And okay, so I talked about Gaudi, I talked about Goya, and I already mentioned about SDSC architecture, but let me just summarize here. So the SDSC's Voyager machine will have is integrated by Supermicro, as I already said. And then it will have 42 training nodes. So remember, each Gaudi node has 8 Havana Gaudi processors, a total of 336 Gaudi AI processor across 42 nodes. And obviously it has the Intel Ice Lake and 6 terabyte NVMe. 2 inference node also with Intel processors and 3 terabyte NVMe. And we also have 36 compute nodes, just regular compute nodes, in addition to the compute nodes that are for the Gaudi and Goya. So, and obviously the 4 gigabit Arista switch with the Rocky. We will have storage, and there even storage we plan to experiment, maybe start out with Ceph first and then do with Lustre. So these are the things you can do on an experimental machine that you cannot do on a category 1. Category 1, we decide Lustre, we stick with Lustre for next 5 years. And I already mentioned the deep learning frameworks of TensorFlow and PyTorch first to get easy port and performance. And then down the road, user will be able to develop their own AI techniques using VOS for Voyager's architecture. A lot of info on their Havana's page. So this is how we have 10 racks. This is the Voyager machine now, 10 racks, of which 7 are the Gaudi training racks. So 7 racks for 42 Gaudi nodes, and then 7 of those, and then 1 rack is for all the networking with the Arista switch, that's the 400 gigabit Ethernet switch. And then 2 racks, always showing 1 here. There are 2 of these that has all the inference and storage and management and all of those. So altogether, there are 10 racks that have been integrated by Supermicro. They built it on their site at Bay Area, then did rigorous testing, and they delivered it to SDSC early November. And since then, we are just bringing it up, making sure everything works. And And it's a new architecture, new hardware, new software. So obviously there is a learning, some things being figured out. If something is not working, we work with Havana to make sure everything working. But we are almost there. In a matter of days, 2 weeks, we will be able to make it available to some of the science use cases that I will talk soon. Okay, so this is just a technical summary. I think all of these are already mentioned, but you can see the memory per node for training, inference, and standard compute node and storage. Nothing new there. Okay, so I will talk about the science use cases because that's a very big part of the proposal, and that's where the actual excitement will happen. So when we wrote the proposal, we talked to all these PIs. Sorry, let me go back. Talked to all these PIs from various science domains, and all doing AI. And most in all cases, either using TensorFlow or PyTorch. So astronomy, atmospheric science, chemistry, high energy physics, satellite, computer science. So these are the PIs with whom we sat down when we wrote the proposal, understood their science use case, what kind of framework they're using, what kind of AI technique they're using, what is their data need, are they doing training or inference, all of these we did. So for in astronomy, so I'll briefly mention a few of those just to give you the excitement that we feel. So the astronomy multi-object telescope data pipeline, this is Alex Saleh from Johns Hopkins University. So he is working on this prime focus spectrograph. That's a multi-object fiber spectrograph. It's probably already developed. When we're writing the proposal, it was being developed and to be deployed on a telescope in Maui. The idea is identifying the faint stars and galaxies that the spectra will obtain the spectra of. And the challenge is there are orders of magnitude more objects in the imaging data than researchers can obtain spectra for in a 300-night survey. And so determining exactly which object will be observed spectrographically and how long it should be exposed. That's the challenge, and that's the research that Alex Saleh and his collaborator in Princeton, they want to optimize the target selection for the PFS. And they have already Bayesian-based approaches, and then they will use a traditional n-body simulation for creating the training set using TensorFlow. And they're interested in the training part of it. And so then atmospheric sciences, we are working with Mike Pritchard, Professor Mike Pritchard, the University of California, Irvine. So basically predicting the effect of anthropogenic aerosols on cloud. And as we learned from him that the global temperature responds to changes in the balance between incoming solar radiation and outgoing long wave radiation. And the largest uncertainty in quantifying the radiative impacts of human emissions on the cloud, on the climate, is caused by interaction of aerosol with clouds. And this resolving these cloud models are prohibitively compute intensive. So he has compared observational data with various cloud resolving models and has one that he is going to use. It's called UPCAM. But that is, again, very prohibitive. He says 60 times more compute intensive than other models. So what he's going to do is he's using machine learning techniques to overcome this trade-off between performance and accuracy. And we see that being done in other areas too, such as in biochemistry and material science. You use a machine learning to capture the accuracy from some highly compute intensive technique which have the thorough physics, and then you use that in real life. So he's going to use a neural network on millions of samples from the short multi-month UPCAM simulations, and use the Voyager for at a small fraction of cost. So that's what his plans are. And then another one I wanted to mention, because we're very excited, because he's a close collaborator of SDSC, we're well known at UCSD, is the human microbiome, the role of microbiome in health. This is with Professor Rob Knight at UCSD. And as we learned from him, that human microbiome is one of the most exciting frontiers, especially with the recent discovery that 50% of the cells and more than 90% of unique genes in typical human body are microbial rather than human. And the key challenge is how the role of microbiome in age-related diseases such as cancer, Alzheimer's, dementia, all of these heart diseases. So he has been using TensorFlow, PyTorch for his research. And given how the sequencing technology has improved, he has access to cohorts both from Asia and Europe, so thousands of people's cohort data. And so basically he uses neural networks to learn the association between microbes and specific metabolites, and that are specifically is interested in age-related diseases. So the goal is to able to provide guidelines for how one can have a young microbiome and then for young metabolism for one's chronological age. So this is interesting. He uses this GAN-trained interface and look at individuals' microbiome to compare how one would look in 10, 20, and 50 years if they continue the current diet and behavior versus if they were to be guided with a microbiome with evidence-based and personal advice. So kind of, I guess, fake your body to behave like as if you were young, even though you're becoming 50, 60 years old, and see how that deals with age-related diseases. Yeah, and then we are working satellite image analysis. I will talk about it. Is with Mai Guen and Ilka. Mai is a co-PI on this project. High energy physics is with Javier Duarte. He's a co-PI on this project from UCSD. In computer science, we're working with a group from Oregon National Lab. They are applying machine learning to data, any and every data that you can think of coming out of an exascale system to predict its behavior, performance, even applications performance prediction. So that's what he is doing. So here, yeah, this is what I was mentioning before. When we wrote the proposal, we sat down with all of these PIs and understood what is the AI technique for Alex Saleh for astronomy, that PFS spectrograph, or for atmospheric science for Mike Pitcher, and then what is the machine learning framework? Are they interested in the training or inference or both on the Voyager machine? So we wrote in detail in the science section of the proposal about each one of them and try to type them to the Voyager machine. Why NSF should fund us so we can work with these scientists initially. And these are not all the scientists. This is all that we can fit in the the proposal. However many pages we devoted to the science application, because we have to talk about everything and the architecture. So yeah, so maybe there's the time. So yeah, these two are. So yeah, Javier Duarte is working with the Large Hadron Collider group at CERN, and as we learned from him that from these complicated detectors, very fast detectors, and petabytes of data are right away discarded when they come out of detectors from experiment like Atlas and CMS, because you cannot store them. There's no space, so you have to make decision right there what to keep, what not to keep, because what you keep then leads to the discovery of Higgs bosons. So he has been working on this for a long time and using various AI techniques for triggering, and then basically improve signal selection. So you you keep the right signals. You don't throw away that can later have a decay signature for Higgs boson. And so they have used both for inference at the triggering point and then later data analysis. And he's going to use graph neural network on Voyagers. He already started porting his model and the modification needed jointly with the Havana team. So he will be a great early science user of the Voyager machine. And then another one I will mention, this is Mai Guen and Ilka, Mai both from SDSC. Mai is a data scientist and Ilka leads the science division at the SDSC. And so here they are, one of the things we all know and can relate to, unfortunately, is the wildfire. So Ilka and Mai have this satellite image analysis tied to their wildfire problem and research effort that they have with funding from NSF. And so here they use it for many other things. So it's like land cover for map generation to aid in wildfire, and then regional interest detection to locate schools in rural areas, even demographic analysis. These are all based on satellite image analysis to see where refugee camps may be, popping up or moving. And this pipeline has already been implemented on the Havana, and I think the porting is probably almost done. So they will be interested in the training. So that would be a good one. Let's see. Yeah, I think I'm almost done. So let's see, this is the, so yeah, Supermicro handed over the machine to SDSC late last year. And these you can see are the, from our machine room, all the Gaudi nodes. And I think this is the one that is the switch. And we are doing, finishing up the installations, system software, application software, and benchmarking. And then we will, then what happens after that is we have NSF review. NSF will tell us the whole story from the day it got delivered to the benchmarks, results we got, and working with some of the early users for a few weeks, which we will start very soon now. Then we'll have the NSF review, and hopefully we'll do good in the review. And then basically we start the 3-year test-based phase right there, and followed by the 2 years of the allocation price. Let's see if I can quickly click on this one so you can see, hopefully you can see the, I will advance. So this is the SMC team and SDSC's operator setting up the machine in early November. I will just fast forward. Yeah, you can see those pictures I showed before, and when it's done, it's very nice and clean. So let me see, get rid of this. Okay, I'm pretty much done. Let me see. Yeah, so as I said, it has been a great working with the application scientists, the Havana team at Intel, and the SMC. A lot of good work, designing, working so far, and we continue to work in the future with among all of us, and get to the exciting phase of actually doing science and looking at the results of a new architecture, purpose built for AI, compared to other architectures like GPUs, and as well as other AI focused hardware like Cerebrus system. And so that's, I'll stop sharing. That's the project, and we are about to embark on actually working with the scientists.
Well, thank you. We have time for questions.
I have a question, Amit. So first of all, thanks so much, as always, for all the resources that the Supercomputer Center gives us to us in the top of the line computing and communication and storage resources. That's wonderful. So I have a question about the the specific platform here. So this is the Intel AI Habana chips, right? And those have gotten some good reviews. Although there's some mixed reviews in the, and it's apparently if you compare apples to apples against other deep learning processors, especially NVIDIA's being the greatest competitor.
Right.
So if you look at, compare the Gaudi against the NVIDIA A100, actually the A100
right.
is about a factor 2 better, right?
Right. I think
and also the there's more resources, more code available, I guess, for the NVIDIA
exactly
framework, right? So what drove the choice of the Habana a platform against some other ones here?
So yeah, so this is the hat, wearing the hat of NSF experimental machine, so we can, so this is what exactly we will explore, right? And see where, is it just the raw performance, is it the price performance, is it the the scalability? So these are some of the things we will explore and compare. And, as you said, with the AI, when we wrote the proposal 2019, maybe the V100s were available, right? A100s were not available. So, so what is Havana's, so, when we have a machine for 5 years in an AI landscape, that's too long, too many new things will come up. Yes. So that question is always, as you say, as you're posing the question is already a question. So, what is Havana's next? What is Havana's next, Gaudi 2.0 or so not that that's part of this proposal necessarily, but so yeah, so we will explore all of those things. Is the scalability good? Is the price performance good? So, Havana, I think they ran their some of their test cases on the AWS, just taking into account the price of A100 was there. So then they say, oh, price performance wise, it's 40% better. I saw this is from Havana.
One second, who pays for that? It was the price for the chip, and there's also.
No, I think what they did was they just pretended they are someone who is paying for a Havana node on AWS and a 100. I'm just thinking, A100 node on AWS. And
yes, because that makes perfect sense, right? So if something is twice more performing, then of course the price, the marketing will just drive the price, right? That's kind of expected, right?
Right, yeah. So those are the types of things we have to explore and see what is the benefit of a, purpose-built AI hardware. And as you said, the software stack is, I'm sure Intel, sorry, the NVIDIA has, is way advanced in, both in depth and breadth. And Havana we'll see how it is. Okay, Mahidar, yeah, I was going to actually call out Mahi to see if he has any input.
No, I just wanted to add that what you see now in terms of performance may not be the upper limit of what you can get on the node, on the thing. They're, like you said, the stack is not mature yet, so they're improving constantly. Even between the time we submitted the proposal with its performance expectations, they've improved dramatically actually between then and now. Like for example, some of the already used benchmarks I think they've gone up by 30% with the same hardware. It's just that their software stack's improving.
Yeah. The other thing is that what is great about it's in Intel AI, there is Intel AI actually based here in San Diego, right? They're
right.
Yeah. And so that opens up some opportunities for working with them here.
Exactly. Yeah. So
I have a question.
Yeah.
It looked like most of the applications that are being considered for this are around deep learning and data science and PyTorch and TensorFlow. Is there any plan down the road, near term or long term, to try and bring in things like neuron and more biological models?
So, the way, this is machine is, and I'll let Mahi jump in or Paul here. Yeah, Paul here. So this is purpose built for deep learning neural network. So I think that is correct, right, Mahi and Paul?
Yeah, so it's unlike, we'll have to look at the code itself to see if there is any possibility, but most likely that would not be optimal on the machine. But that said, there is an API that is a lower level API that you can develop code with. So you don't necessarily have to stick to PyTorch and TensorFlow. And I'm sure we'll be looking for some use cases that are like that, where somebody might have a custom way of doing things but eventually I think everything comes back to a deep learning specific thing. So because it's essentially a chip for that. So I think
it won't be available for NSG users, the Voyager machine.
Sorry?
So it won't be available for the NSG user, the Voyager machine, or we can also.
That's true. Yeah, this is only for deep learning applications. As initially, like Mahidar said, unless it spans out into some other neuroscience applications, which are maybe custom those people, researchers, neuroscience researchers, can custom write to take advantage of the architecture's performance, it will, it will not be a good fit.
Okay.
So that will be
Okay.
something we'll explore down the road. Initially get TensorFlow and PyTorch, and then Paul, Paul actually wears neuroscience hat, data science, all kind of hats.
Yeah, that's my basic understanding. But I think, I mean, I think as time goes on, I think Habana is trying to get more variations in the deep networks that they could optimize and run well on their machine. So I started out with an example of a recurrent network in TensorFlow, and they didn't have that kind of graph. There was graph that comes out of that optimized yet, but that's the kind of thing they're working on right now. So I feel like if you're doing a neuroscientific model and a neural computation based model in TensorFlow or that kind of level, I don't know if you guys, people are interested in that kind of operation level. It's probably not ready for that yet, but I think more of it will be.
And I'm just wondering if the architecture is amenable to spiking networks in general, for example.
In that case, I think, I don't know that it's so much the spiking issue as maybe the connectivity issue. If you're looking at large sparse connectivity, that might be more of a question than whether you're simulating something with a finite model.
Okay.
But I think that's a good question. I think we will be getting more experience on.
Thank you.
It is experimental, so that is one of the things that we'll have to do, I think, is to kind of see, explore the limits of what we can do with the machine.
Yeah, we're just going back to what Gart was saying. Mahidar actually ran the all reduce and all to micro benchmarks across the communication library, and they're showing, like you said, not orders, but 30-40% better performance on the all reduced latency bandwidth compared to initial numbers we had or thought of maybe 2 years ago. So yeah, Havana is, Havana fully aware of the question Gart asks and working hard to improve performance, the software stack based performance.
Any other question?
I could ask you another brief question for expecting a brief answer, but not being familiar with the Habana processor architecture, when you talk about modifying things at a low level with the APIs, are you talking about writing code or microcode or RTL?
You can actually, I think there's a C and a Python API, so you could write it in higher level language. I mean, you don't have to write microcode. So there's,
all right.
But I mean, there is a subset of functions that are supported. So as long as you know how to make use of them, I think you can write a C API. Yeah. I mean, C code.
Okay. Thank you.
In fact, I think the all reduced code is probably in C.
Mm-hmm. Okay.
Well, thank you, Amit.
Sure.
I think I will close now if no one has done as a question. So just go on, done. Oh no, he's just uploading. Okay, sorry.
No, thank you very much. Very informative.
Yeah, thank you.
Looks like a cool machine. Thanks.
Yeah, thanks for giving us the opportunity to talk about it. And we hope to work, maybe some of you will be interested from different angles, like you're asking questions already, which would be great. So.
Do you have any
Thanks so much. Thanks, Amit. Thanks, everyone.
Yeah. Thank you.
Thank you, Nick.
Thank you.
Yeah. Bye.
Bye-bye.